Okay. Goal for today is kind of wrap up project 2 with our like 4-bar linkage. It's kind of like an reverse engineering sort of project. You could also do kind of forward engineering, but one way to approach this is like, I know this 4-bar can do this sort of thing. I've seen it exists, like windshield wipers. Like, we know windshield wipers work, and inside there is this 4-bar mechanism working. So it's a reverse engineering to figure out how do you set it up so that it actually does what you want. You could also do this in a way of like, oh, wouldn't it be cool if this thing, like someone was thinking like, could I create an automatic catapult of like, it flings something every rotation, every like crank rotation, it'll like launch something. So they were trying to like maximize that theta 2 dot, because if that's max, then you get max speed kind of launching off. And that's another way of like forward engineering. So I would there's probably like general questions of like how to do this, what are we supposed to do? But there's probably also like individual questions of like, I'm trying to do this, but it's not working. I gotta plug in my computer. So, does anyone have, what either general or specific questions are there so far about like doing the project? Everything's going swimmingly. No issues. There's got to be some issues. Something's got to be broken. There's got to be like, how do I turn this in? Or, no, everyone's just like, yeah.
What do you want us to download it in? Because if I try to download it as a PDF, HuskyCT says it's a security alert.
Oh, security alert? What do you mean? When you say...
It shows up whenever I get a PDF.
Yeah.
It says that it's a security threat, as well as if it's in HTML and Python.
So usually HTML works fine. In HTML, you can print to PDF. I haven't seen security alerts. I've seen the thing that I thought you were talking about was a lot of times if you try to download via LaTeX, then it'll come up with this like 500 server error of like something in the background went wrong. So there are ways to fix this, but then you have to do like LaTeX troubleshooting, so we don't have to worry about it. HTML or a print preview is fine. So like file, print preview, and print preview and an HTML are the exact same document. They're both showing the same kind of thing. But yeah, I haven't seen like a HuskyCT issue yet. Maybe if you're running like inside the HuskyCT browser, like rather than a new tab, like in your own browser. I don't know. There's also like, so the main thing that you're doing here is like, you're choosing some design variables to get it to work, but you also have to think about like, why is this a working design? And that's what I wanted to kind of help out today, figuring out. It's like, you recognized it, maybe it looks right or it feels right. So how do we actually describe that these are the things that I'm showing that's right? Right now, the simulation that I have, like nothing looks right. So if I was going to write a report about this, it would be how I didn't choose parameters that are working. Like my design is not working at all because I'm breaking constraints in this hinge C, the motion is not smooth, like there's just stuff going wrong. But we want something like kind of going right. So I bring that up because some people prefer to write kind of reports in like a Microsoft Word or Google Doc or something. So if you want to do that, you could have like, here's the analysis, and then copy these images into your report, and that's fine, as long as you have like the background code like as another file, so you could submit like a document and a notebook, or just the notebook, just write everything in there. That one's just like a logistic. What else came up? I know there's something. I'll ask around, because there's got to be more going wrong. It's always something. How's it going? Yeah. Oh, cool. Yeah, yeah. Nice. Yeah. Okay.
So I'm not really sure what went wrong.
So it's probably, if you scroll back up to like these tabs, the next one down. So right now, is there a reason that these are, like your O and C are not? Where did you want O and C to be? Like where, if you think about like what you're calling the ports.
This, I'm gonna put this, so this I want in the ACL, so this is L1.
Yeah.
And this would be L2, and then this would be L3.
Yeah.
So, I don't know, is that different from what we did?
No?
I didn't think I needed to change where, like,
So like where, yeah, like where's A? So here's A, B, this is O, and C.
Yeah, so this would be O, this would be A.
Yep.
And then B and C.
Yeah.
So I want to go in the same spot.
They're, yeah, like as far as like the geometry, they're in the same spots. But it looks like it was almost like 45 degrees between O and C. Like way up like that. O and C.
Yeah, we don't want to do it.
C, yeah. So we're just looking at like the ACL, PCL kind of simulation. And I think a few people were kind of looking at a similar thing. And the graphs look all wacky. Just like stuff is breaking, like not what you want your knee to do. So what were the lengths here? Like L1, what did you have? Like 3.5 centimeters or something?
Yeah, that's it. 3.3.
And then
33 millimeters, 32 millimeters was L2, and then 36 millimeters was L3.
36. And we can, like as far as the analysis is concerned, like we can use whatever units we want. So we can say 33, 32, 36, and that's fine. Let's come back up here. So, oh, yeah, it would help if I'm actually in. So 33, 32, and 36. So then what about like where, like if this is 0, 0, where does C belong? Like I would think it's 32 millimeters away, something like that. Like I could call my DX 32 millimeters. Maybe something like that. So let's say it's 32. And I'll leave dy as 0 just for now, just so I have like something. But you could change dy if you want, like if you have better estimates for that. All right, so our first like same thing that happened on Friday, like we got a big pink warning. Again, it's a warning. It does mean that it gave us answers, but probably the answers are not what you wanted. And if I look at like what the motion is, something's a little weird. And then look at the paths. It's kind of like things are breaking. Like point C is moving around in a circle. And part of that is that like this should really be like over here, right? Like right now it's kind of a parallelogram, but we want it to be crisscross, like ACL, TCL, kind of crisscross. That has to do with our initial, because really there's two configurations that work. Like we can either have parallelogram or like a crisscross sort of thing. So I can try changing, like if this, yeah, two things that we want to change. One is the range of motion. We don't want our knee doing a full 360-degree rotation, so we want to limit how far we're going. So let's start with that. We have A1 defined. Let's just go from like pi over 4 to pi over 2, something like that. So 45 to 90, and we'll go every degree. Now it's looking like a little better, like we see a little closer to what we were trying to get. But I want to change it so it's like flipped, so it's crisscrossing. So if I'm starting, if this is like 45 degrees, this angle should be about 180. Like maybe not exactly 180, but I want it to be something where it's like flipped upside down. And then this angle, number 3, should be like more than 90. So let's call it like 100. So we just want to, as long as we're in the ballpark, like we'll converge to a solution that works. We want to get somewhere. But that's why I think it helps to draw it out of like, what am I actually looking for, and then start solving for. And this could help like a lot of people. If you're close or you feel like something's wrong, try to just sketch out what you're trying to do and then go from there. So right in here, we changed A1. A1 is only going from 45 to 90 degrees. So it started at 45 up to 90, so it's only that 45-degree change. I want to change my initial guess for theta 2 and theta 3. So I want this to be like pi, and this one maybe pi over 2. So it's trying to get bigger. Or even like pi and pi would probably be fine. But I don't want 0. I want it to be bigger than that. Let's do like pi over 2. Kind of better, right? So this is showing me like the 90-degree. And that one's 45. So maybe we don't want like 45, maybe we want to make it like even smaller of an angle. Or maybe the where it's mounted is like too far apart, so my ACL, PCL are too close together. So maybe I want to make that DX a little smaller, if that makes sense. But I am starting to see like actual knee, the knee shape here, that like green line, and I'm not breaking my yellow like UC location. Yeah, so let's go, just so it looks a little better, we'll go like pi over 6, let's do pi over 10 up to pi over 4, and I'm just gonna leave it, it's like, so now it's just a little bit of that motion that way. And now we see like a little bit more of that ACL, PCL, like crisscrossing and kind of moving up and down this way. But again, main thing here, sketch out before you just like hammer away number, like numbers and code helps to figure out like what am I actually looking for here? Start with a sketch or an estimate of where you want to be, and then we can go from there. Other things, trying it. Did that help to limit like range of motion? Okay, yeah. Yeah, yep. And really, like, every person has a different ACL, PCL. Yep. Cool. Yeah, so driving, like if you're doing windshield, 2 seconds. The dry rate has to be 1 cycle per 2 seconds. No, because I mean, if you can, if you want it to be like a really precise metric, but also that one is kind of designed originally, because even in heavy rains, the light rain kind of scale. The main thing there would be like if you were driving half a cycle, probably 50 radians per second to get 1 meter long, which is like 3 feet long. So 50 radians per second times 1 meter, that's now 50 meters. 100 miles an hour, which would be way too fast to be swiping the rubber. So you have to change how things are. Still want to down half hertz, but we want to have like a reasonable, maybe 10, maybe 10. That'd be one of the things, one of my design constraints. Yeah, you can change like they're all similar. You can play it. And that's what the question is about. If you change the amount of stations, what or whatever you play, I can help you with the we found like a set of constraints, set of like lengths that won't, by the time you get up to your 90, there's like 180. You can't. Oh, because this engine, how do I change the lock? DX and DY say from low to speed. But also, L2 and L3, if you add those together, they have to be less than L1 if you want to do a full 360. Why is that? Less than. Well, I guess like L2, L3, and then like L1 and L2. I mean, you can play around. If you don't trust me, you can try. L1 plus L2. Sorry, L2 plus L3. Oh. Okay. Yeah. Yeah. Yeah, and there's a specific like ratio constraint. There's some things That's even before coding. We didn't code anything until we figured out what we wanted.
I figured well after I got parts and stuff, I just wanted to use that to request about it.
There we go. Yeah, it's coming. With the high cycle fatigue problem, ACL is low cycle fatigue.
Yeah, I never walked into that.
Oh, you
I'm
know,
super into cars, so I know like a bunch of
Yeah.
suspension setups. This is something I've never.
oh yeah, try it out. Because lot linkages are so cool.
Yeah.
Because you can have like big range of motion that's completely virtual.
Right.
Which is great. Like instead of piston and adding friction.
No, I was just trying to think, like, I always think of it from suspension system. Everything is out. Like, there's no way you can do without it.
Yeah.
Here's another.
There you go.
I was trying to replace
Oh yeah, yeah. Okay.
I was trying to figure out the
Mm-hmm.
and this would be, I would rotate it this.
Yeah.
I think it would work. Like, this wasn't, when I would put in dimensions,
Mm-hmm.
can't find any dimension. But, I had it, it was like, this was like,
So that's like O and C.
yeah, so
That's maybe.
so, well, yeah, so I had that, the long one, was 39, and then this was like 35 or something, or maybe this was, that was like 35, but like 3 inches and a half, this was like 4 inches, and then this was like, 6, 7, I got like this, and I was just like, couldn't figure out how to get, like, the long part, because when you're trying to, on the short bars, it wasn't. Yeah, I was thinking maybe we used to like start doing like this bar back up. And how the motion would look like. What are these? Those are, that's this here. AED. So this is the current geometry. Because I was struggling to get it to rotate like directly here. So this is what I so when I tried to use it with this, it would just throw me an error. It wasn't sure.
I mean, you're right, like, the whole thing sort of like is one rigid body, like you can put it in any orientation you want. But it's okay to say, like, okay, these two are fixed, and then just rotate around them. Those two are fixed.
Yeah.
Yeah, yeah,
Would that make sense?
I think it would. discuss a little bit about lockers.
Okay, cool. Yeah. You might be taking a quiz like after, just so I can check in, make sure projects are.
My thoughts are just
Yeah, you should be. Yeah, so it looks like this, because this one is theta 1, L1. So 90 is sort of minimum, so maybe it'll go up to, or sorry, 20. Oh, 180, maybe it goes up to like 135, down to 200. Another range of motion that you can talk about. And then you can then what you can do is really play around with like these, like one thing you could do is this one parallel, and now you'll always be 90 degrees, or the way that we have it drawn here, maybe it'll have a little bit of camber that you're going to know, so maybe that's what you want. But yeah, that's what engineers do. Compare routes like that, right? Try a few, and then at the end you say, right, this one is what I want because I want camber. All right, so I'll check in again on how things are going, but I wanted to talk about, like, especially for wrapping up, like there's like some general things of like, okay, plot the motion, like some of that stuff is sort of filled in, but everybody's analysis is going to be a little bit different. Like in this case where we're looking at an ACL, PCL, we probably care mostly about the motion of the knee, like how, like when I'm coming up to here, like what is this green line doing? And that's a lot of like, if I'm thinking about knee replacement, or if I need to shorten that, like if there's an ACL tear and I need to shorten it and reattach them, how does that affect that green line or something? Like that's like one thing that I would think about. Or even like these angles here, like what is the range, what is that range of theta 2 motion? Because ideally theta 2 can kind of go from 180 up to, I don't know, 270. Like you want to be able to bend your knee 90 degrees. And so that's what we're kind of looking at this one. It's just, it's a little inverted because really like theta 2 is kind of the driving thing, and then theta 1 is just a consequence, just happens to be connecting them. So, but that's what I would kind of talk about here. It's like, look at my range of motion for this ACL, PCL simulation. Right now I go from 170 up to 215. So I have 45 degrees of motion simulated. And in that range of motion, I have this green line that's defining the path along my, like, along the femur, like what the connection needs to look like, what that joint looks like. So those are, like, always work on quantifying your engineering, and that's a really hard part. Well, it should be easy because we deal with numbers all the time, but it's hard to creatively quantify things because that's what you're doing here. It's like trying to tell a story with numbers. That's the goal. Tell your story with numbers. So choose some numbers, and then same thing. Like we can look at like motion. Like as we're bending the knee, so the knee is kind of moving at 1 radian per second. Our theta 2 dot and theta 3 dot, like how fast are those things moving? And here we have like 2.5 radians versus 1.5 to 1/2 radian per second. So there's nothing, it would be bad if you're bending your knee at 1 radian per second and everything else is changing at 100 radians per second. So if they're all within the same order of magnitude, everything's probably fine. But if there's big changes, then that means there's either like a big release of energy or something, like something big happened. Maybe you want that, maybe it's the knee of a grasshopper, and that's okay. But here at least this was a human knee, like roughly humanoid. Anyway, just some tips on like how to like take the graphs that we're creating. If you need other graphs, like I can help you, like if there's something that you're trying to say but you're not sure how to get the data, it is there, like we have a full simulation. But at least you can start with these, pick out some data points, like usually range is a big part, magnitude, and yeah, other things like that. So that was my general advice. Yeah, like that one. That's okay, so that's fast. That one. So what is, let's see, like the paths of motion. Something strange is happening there. It is kind of moving fast, like snapping. Yeah, I wonder, like I know like from your research, I don't know. So what are your about
Yeah.
part of it is that we're assuming phase 1 is the driving lane, but really it's phase 2. So usually your ratio is
say speed 1 is bigger than speed 2. So it would be for every one rotation of gear 1, you have, say, 2 rotations of gear 2.
that would be like 2 to 1.
That would be a 2 to 1. So then saying this here, a 1 to 5, would that be an accurate way of saying gear ratio?
Usually just the inverse of it, probably 3 to 1, 4 to 1, something like. Unless you like on gear down, you're saying like it's like 1 to 10. That means like I move once, and I've only moved a 10th of a rotation on my output. But usually still what's your input to output. And in this case, one light rotation is
So you for every rotation of this, you just rotate once or something like that?
Because I think it ends up being 3 or something to 1, right?
It's just about 3 to 1. Well, it's 10 over. I got 10 over 5. It's just about 3 to 1.
Yeah. That's mostly physiology too, which is crazy because you guys are 3 words. Next semester. Oh, cool. You guys are great. Yeah, because you have kind of a fixed thing for
Hey, I just wanted to see if you could check over. Well, I was not checking over.